Hi, my name is Adela Week.
Jeff Michonne.
Joe Brown.
Kunal Patel.
Jeffrey Wilder.
And today we're going to talk about our RBE501 Robot Dynamics project, where we developed a device for finger pose estimation. Hand rehabilitation is the most common form of occupational physical therapy brought on by either medical conditions such as stroke or repetitive stress injuries in the workplace. The majority of measurements used to evaluate dexterity either use protractors or goniometers for measuring joint angles, or they use devices that measure joint flexibility indirectly. Current devices that are used for rehabilitation seem to measure angles indirectly, such as the Amadeo, which is shown on the left, which uses levers that the patient operates, and the Music Glove, shown on the bottom right, which monitors if a hand is in a specific position, as opposed to direct measurement of the joint angles themselves. However, many of these devices need to be used under supervision, which usually means a trip to the hospital. Having a system that doesn't require intensive calibration and can be used at home would make this a very practical device. In addition to rehabilitation, we also came up with some other possible applications. They are comparing finger dexterity efficiencies across various tasks, such as comparing musician skill or that of a hobbyist knitter. Our goal here would be matching end effector outputs for different size hands, at which point we would be analyzing inverse kinematics problem. Another application would be fabricating a customized board or object designed to the limits of the joint angles based on what we determine through inverse kinematics. Yet another possible application would also be to control a serial manipulator with a matching number of joints and develop a glove that we could map over to an existing arm for teleoperation purposes. The purpose of this project was to create a dynamic model of a finger and use off-the-shelf technologies to create a reliable glove-mounted sensor system that was able to give reliable angular finger joint measurements. Our current system consists of 4 IMU units, which are attached to the fingers via adjustable rings and a GUI that displays the finger motion and records the motion for inverse kinematics analysis. Using the optical tracking system in the AIM lab, we verified that our Adafruit IMU sensors were accurate enough for rehabilitation monitoring purposes. In the next section, we'll go into the design and fabrication of the system, as well as the analysis we performed on the data we collected.
The mechanical systems developed for this project included a 3D printed finger model. This was based on a model provided by the AIM lab, but redesigned to include an additional degree of freedom to account for lateral movement of a finger, as if someone was wagging their finger back and forth. For implementation on an actual human hand, we designed and 3D printed ring mounts for the sensors of different sizes that can be slipped onto finger segments of various sizes over a form-fitting glove. We also designed and fabricated a box that is attached to the forearm to hold the microcontroller, allowing for an independent and mobile system.
Here's a look at the system from an electrical hardware standpoint. The microprocessor handles sensor initialization, calibration status monitoring, and at the request of the MATLAB script, reads each sensor's quaternion orientation over I²C, converts the orientation to ZYX Euler angles, and transmits the result to MATLAB via a serial link. The LCD aids the user in performing the initial calibration and shows the status of the microprocessor. The I²C multiplexer solves I²C addressing issues with the sensors, providing them each with their own bus so that they can all use the same address. The IMUs we used are from Bosch, the B&O055. These sensors are neat because they combine an accelerometer, gyro, magnetometer, and an ARM microprocessor which runs a data fusion algorithm all in the same board. This allows the IMU to output its absolute orientation with respect to a reference orientation, which, once calibrated, is the same reference for each IMU. The onboard microprocessor also handles calibration of the sensors in a process that is completely transparent to the user. Our system reads the calibration data upon initialization of the sensors and waits for the sensors to calibrate before allowing data capture. So given the absolute orientation output of the sensors, how do we find the joint angles? Once the sensors are all calibrated, they lock onto magnetic north and start outputting their orientation relative to the same reference orientation frame, X, in the diagram. The Euler angles from each sensor reading are converted to the rotation matrix they represent, which is the rotation matrix defining the orientation of the sensor frame with respect to the reference frame. From there, it is simple to solve for the rotation between the sensor frames using a little algebra. Now all that's left is to find the joint angle. We notice that the rotation between frames M and N is limited to the y-axis of frame M, and is therefore a fundamental rotation about y. So we can solve for Q by taking the arctangent of the appropriate terms in the rotation matrix. This method works for joints 2 and 3 as is, but the first joint is slightly more complex since it has 2 degrees of freedom. The method is the same.
A forward kinematics model was created using the DH conventions to show the position of the finger in 3D space. The left image, which we'll call the robot frame, shows the pure DH representation of the finger. However, this orientation had the x-axis pointing upwards. A more familiar coordinate system was used where z was pointing upwards using 2 additional DH rotations. This brought the model into the world frame seen in the center. The conversion between the 2 frames can be seen on the right. The series of transformation matrices allowed simple visual representation of the finger. The joint angles determined in the previous slides served as variable inputs, while the lengths of each finger link served as inputs that did not vary with time. By determining the translation after each transformation, a vector of x, y, and z points was created that was plotted using the plot3 command in MATLAB. Of course, matrix computation is not as fast as more direct methods. The x, y, and z vector computation was optimized by symbolically determining the values after each transformation matrix multiplication. This symbolic expression was then used directly as seen at the bottom of the screen. Similar optimizations were made in other areas of the code.
The first step is to select your COM port. In this case, it's COM5. If you ever need to check for new COM ports or update the list, you just press this little button here. Once again, it's the same. The baud rate by default on the microcontroller is specified here, so we're not going to change that. You can change the link lengths over here, which will change what shows up in our 3D space over here. This is the orientation of the sensor, just for reference. And the measurements will show us the x, y, z position of the tip and the angles Q1, Q2, Q3, and Q4. So we're going to connect to the device now. In order to do this, the sensors need to calibrate, so wiggling them around will usually calibrate it. And we're connected. So to start displaying the output, we press the Start button. And you can see the screen updating here. When you want to stop recording, you just press stop, like this. And for this case, we will save our recording. So we'll click Save, and we will name it Data List. That sounds like a good name.
Our next goal was to demonstrate another finger with different digit lengths, reaching same tip position as that of the recorded finger. This is achieved using inverse kinematics to solve joint angles of the new finger for a tip position at given point of time. We implement the inverse kinematics through lookup table instead of solving the kinematic equation every time a tip position is queried. The lookup table generation needs to be done only once for a given digit length, and searching the lookup table is much faster than solving inverse kinematics problem. The lookup table is generated for joint angles with 1 degree steps, which was sufficiently close to queried tip position. The lookup table generation is made fast using MATLAB built-in functions effectively. First, we create a 3-dimensional mesh grid of all joint angles and calculate corresponding 3D matrix of x, y, and z coordinate of tip for the angle values. Then we generate a list of matrix or table which with each row containing array of the tip coordinates before the joint angles it maps to. Then we use sort row function in MATLAB to sort this table with respect to x coordinate as priority, followed by y coordinates and z coordinates for sorting priority. Then we return this sorted table as our lookup table for given digit lengths. Once we have our lookup table, we just need to search the joint angle values for given x, y, z tip positions. To do that, we first start searching for matching x coordinate in lookup table. Once we find a close match, we switch to matching y coordinates and then z coordinate. After locating a row in lookup table with closest x, y, z coordinates, we fetch the joint angles in that row and return them to the plotting function. The demonstration of the process is followed.
In order to play back this data, we go to Playback and we load the recording. So we're going to load the data list file that we just saved. Click Open. You can move the slider around and show the playback at different times. Time is specified over here, and the joint angles that were given at those times can be seen down here. If you want to use the inverse kinematics lookup table that we created, all you have to do is click on on in the inverse kinematics section, and a table is created. This table is based on the lengths L1, L2, and L3 that you specify before clicking on. If you want to change them, turn it off, change them to say 12, 12, and 12, and generate a new table. Once you do this, a red arm that represents the inverse kinematics will show up. And you can turn it off just the same way, and back to the original recording. You can disconnect the device by pressing the disconnect button. There we go.
Using the vision tracking system in the AIM lab, we were able to verify that our sensors are fairly accurate. Tracking nodes were placed on each of the pivoting joints of the test fixture. The XYZ location of these nodes should be directly related to the positions determined in the forward kinematics model. It was predicted that because the device is essentially a series of links, the error would compound over the length of the device. This is an issue that would not be present in the optical tracking system because it determines each node position independently. The 3D printed test fixtures seen in the images had link lengths that were proportional to humans, but were slightly oversized to allow easier mounting of the sensors. Link 1 was 57 millimeters, Link 2 was 49 millimeters, and Link 3, the final link, was 42 millimeters. It is important to also note that the test did not measure rotations about theta 1, as the test fixture did not allow the joints to be coincident, as on a human finger.
Two types of analyses were performed on the data. The first was comparing the measured joint angles. Since the optical tracking system only gave results in X, Y, and Z, the values needed to be converted to rotations. Once this was performed, it was shown that the MATLAB computed joint angles were only off by 5 degrees at joint 2 and 2 degrees at joints 3 and 4. It was noticed that there was an error converting angles below 0 degrees. Negative values showed up as their positive counterparts. However, in analyzing the positive components, the results seemed fairly consistent, and it was concluded that the negative values could be ignored. The second analysis performed compared to the heights, which we measured in the z-axis of the joints. As expected, the error accumulated and resulted in the tip and joint 4 being off by 4 millimeters, while joint 3 was only off by 2 millimeters. Joint 2 never changed, so it was not shown in this graph. The benefit of this analysis was that there was no conversion needed between what the motion capture system detected and what the device software detected. In addition, it is assumed that the joint positions are more relevant to medical studies than joint angles. This is therefore a more representative test of performance. The conclusion drawn from the testing is that the motion tracking of the MATLAB software is relatively accurate. The results indicate that the joint positions are within 1 centimeter of their actual positions as determined by the optical tracking system. However, it is important to consider that this was tested only with a rigid finger model. Correct placement of the sensors on the glove is critical to achieving similar results. The testing has also shown that there is no noticeable lag between moving the sensors and the MATLAB 3D representation. This was initially a concern considering the computation occurring as the data streams in over a serial connection. Finally, the lookup table based on inverse kinematics solution has proven to be both fast and effective. While the inverse kinematics of this particular device aren't impossible to solve, they were quite complicated. Learning to implement a lookup table for such applications was very valuable. Future work will include implementation of these sensors on a full hand with a refined design for mounting the sensors to the glove more permanently. We would also like to conduct further testing on our device beyond mere mobility, such as gesture recognition. As previously mentioned, this project could be applied to hand rehabilitation, so we would like to test this device with the motions that would be done as part of rehabilitation exercises, and also with a patient undergoing such rehabilitation. Further implementation of this project would also include optimization of the software, having more calculations being performed on board. This would allow for real-time performance without being tethered to a serial port. The implementation of a Kalman filter would also refine the measured motions of the finger joints.
In this project, we developed a functional kinematic model of a human finger in MATLAB that can be interfaced with both a mechanical test fixture and a real human finger. We created a wearable prototype sensor embedded glove to capture the motion of a human finger. We also developed an effective method for computing inverse kinematics for a finger of different lengths to reach the same point as the initially recorded finger. We have verified the effectiveness of this system by comparing it to a reliable optical tracking system, showing that this measurement device is a viable solution for finger pose estimation and its applications.